Okay, good afternoon. My name is Alan Jen. Can everyone hear me in the back? We good? All right. So. All right, I will try and project. Hopefully you guys are all in the right class, Intro to Electric Vehicles. This is the first time this class is being offered. So we're pretty excited. Yeah, so just to introduce myself, I'm a research faculty with the Institute of Transportations. It's one of the large research institutes regarding sustainable transportation in this university and actually across many universities. And so I am in charge of this course alongside Dan Sperling. Do you want to maybe introduce yourself real quick?
I'm mostly interested in the policy side, so when we get to policy,
yeah, and so that'll be more sort of at the end of this course. So we are in civil and engineering officially, but this is going to be a pretty interdisciplinary course. So we will be covering some sort of engineering aspects of electric vehicles, but we'll also be talking a lot about some social sciences things related to electric vehicles and policy, of course. Okay, so because I haven't taught this course before, I'm kind of curious about the demographics of the course. So who here is a first year? We have one. Second years, third years, a couple more, fourth years. Oh, a bunch of fourth years, great. And then grad students, a couple of grad students, great. All right. Oh yeah, who's from civil? Mostly from civil, mechanical, environmental sciences. Okay, and then everyone else, anyone else? What are you guys from? Energy, EGG, awesome. And what about you? Computer science, awesome. All right, great. And hopefully there's going to be a little bit of everything for someone here. Okay, so the first thing we're going to do, we're going to go through our boring old course logistics. If I can get my slides working. Okay, so class logistics. Everyone is here right now, so we'll be here in the future. So office hours, I'm going to be having my office hours Mondays 10 to 11 by Zoom. But if you do want to meet in person, you can go ahead and just schedule with me by email. All of this information is available on Canvas. But you're welcome to reach out to me at any time. During the course, there will be one holiday, which is on May 30th, Memorial Day, so there won't be class on that day. Okay, COVID protocols. So I guess official university policy means that we don't actually have to have masks anymore, but we'll still encourage it. I will be masking. If anyone wants the mask, they are totally welcome to do so. But you are required to do the testing every 2 weeks. So please make sure to do that. And don't come to class if you are sick. Goes without saying. Okay, in regards to hybrid or remote teaching, so we're not going to do hybrid mode. So there's not going to be remote attendance options, but I am recording the lectures and they'll be available and posted on Canvas and on YouTube. So if you miss a lecture or unable to attend for any reason, feel free to catch up by watching those. All right, I'll pause for a quick second in case anyone has questions. Yeah.
In the course, this says participation rate 20%. So how does that work?
Yeah, so these are just for like makeup purposes. So what we're gonna do, actually, I'm gonna get there. We're gonna have a slide on that. So yeah, I'll talk about participation in just a second. Anything else? Cool. But thanks for reading the syllabus already. Schedule overview. So this is an overview of the topics that we're going to be talking about. I put together most of the material already, but if there are things that folks want to get more in detail into, or the class is particularly interested in, you guys can let me know. We can sort of readjust some of the material, but this is kind of what it's going to look like for now. So the first kind of set of stuff is going to be more on the engineering side of things. So we're going to be looking at the drivetrains, the battery technology, things about efficiency of the vehicle, and about charging infrastructure. And then here we'll get some more into sort of social science issues, looking at preferences for electric vehicles, how people use them, how people are charging. Over here, we'll look at some environmental aspects of electric vehicles, how they relate to the electricity system, how they relate to air quality, pollution, and greenhouse gas emissions. And then, as I mentioned before, we're going to look at a host of different electric vehicle policies, both in the US and across the world. All right, any questions here? Okay, so participation, as someone was asking, it's basically free points. I guess we have about 20 lectures and it's 20%. So each lecture you show up, it's free 1%. So what we're going to do, not today, but for the rest of class, we're going to keep track of attendance with online polls at the beginning of each class. And so you can just put your name down, and then we'll ask some kind of questions regarding the topics that we'll be talking about that day. Get a sense of what people are familiar with, hit any sort of misconceptions people might have. Okay, homeworks. This is going to be the bulk of the grades for this class. It's going to account for 50% of your final grade. There's a total of 4 homeworks that are spread throughout the quarter. Yeah, and it'll be divided into sort of a quantitative and qualitative section. And lastly, we'll have a final paper, which is going to account for 30% of the final grade. There's 2 components to this project. There will be proposals that are due mid-May. And then the final project report is due on June 8th, which is like halfway through finals week. We'll have a couple more details in the future, but the paper is supposed to represent kind of a deeper dive into any of the topics that we covered during class or something related to a topic that we cover in class. And we're really going to be looking for reviews of studies that people have already done, as well as thinking about sort of policy regarding any particular topic. And obviously, this is going to be sort of nuanced depending on what you guys will be looking at. Yeah, and we're looking for groups of 2 to 3 people per project. So the proposal is still quite a ways off, and the due date for that is going to align with kind of the start of the policy lectures. So you guys will have time to hopefully digest some of the material that we're going through as we go through the course, but start thinking about topics that are of particular interest to you guys. Okay. I was thinking about organizing some kind of ride and drive, but turns out there's going to be a EV showcase happening on campus anyways. So on picnic day, which is April 23rd this year, there's going to be a community organized event, basically where a bunch of people who own electric vehicles have been asked to see if they want to volunteer showcasing their cars on campus. And so this is kind of a nice real world opportunity for folks to check out vehicles in person. And we'll probably offer some kind of bonus extra credit or something if you go. Yeah, who's actually driven an electric vehicle before? A couple people? Great. Who's ridden in an electric vehicle? Okay, a little bit more. Awesome. yeah, so this will be an opportunity to do that if you haven't done that before, or get exposed to a whole range of different types of electric vehicle models. All right. The last announcement that I'll make. So if you are really interested in this kind of stuff, there's an internship opportunity with the National Center for Sustainable Transportation, which is one of the sort of big centers that helps support the institute at our campus. And so I put the link here. I'll make an announcement, and you can check that out if you are interested. And so this is a summer fellowship. And I think this is specific for undergrads, but yeah. Okay. So why do we care about electric vehicles? So I have kind of some of my own reasons, but I'd love to hear maybe some of yours. Dan, maybe I'm going to put you on the spot. Why do you care about electric vehicles?
Okay, so electric vehicles are the second best way to greenhouse gases. The best is decarbonizing electricity. And it's by far the most important one. On top of that, reduces air pollution, so those are the main ways. And as it turns out, it's also really cheaper to own and operate. It will be about 4 or 5 years cheaper to own and operate than gasoline vehicles, and not just part of the price. And so it's better for the economy, better for the environment, better for the future of humanity.
Yeah, great. Awesome. What about you guys? Who is here because they like the sort of environmental benefits of EVs? Okay, a good number. What about the sort of new technology aspect? Bunch of people. Yeah, and then sort of the economic part of it. I don't know if people actually care about that right now. No, all right. Well, when you are out in the real world and you see $6 a gallon for gasoline, I think maybe that'll change some people's minds, especially these days, right? But yeah, so I'm just gonna kind of echo kind of the motivations that Dan was talking about. So for me personally, emissions and climate change is really how I started to get involved in this area. So anthropogenic emissions of GHGs, so greenhouse gases, are leading to a bunch of impacts at a global scale. And essentially, in order to do that, we have to, in order to mitigate the issues related to climate change, you have to lower emissions. And transportation is one of the largest sectors, if not the largest sector in sort of many economies when we think about this, this issue. And so, you know, electric vehicles, there may be some perception about they might be a little bit more expensive, right? And we'll talk about that in a lot of detail in this class, right? But also the damages from climate change are also going to be very expensive. And so it's probably better to try and reduce some of these effects, right, than not to address some of the issues related to climate change damages. Already there's a lot of work looking at sort of the economic effects of climate change by income. And one of the things that we'll kind of touch on throughout the class is this disparity in effects for a lot of these impacts on higher income populations versus lower income populations. And that's going to extend all the way to even thinking about electric vehicles. So we'll keep that kind of theme in mind as we talk about electric vehicles. Okay, so I had mentioned that transportation is a particularly large portion of emissions. So here, what we can see are the energy use emissions by sort of end use sector. And so in energy, you can see there's a portion here, transport accounts for that portion. With it, so this is worldwide. Here we have for the US. So a decade ago, actually, the largest contributor to emissions is electricity. But because of cheap natural gas prices, that caused natural gas power generation to displace coal. And so this sector started to decrease quite a bit over the last 10 years. And that now means that transportation is the leading sector for emissions in the US. And then here, specifically in California, because our electricity sector is relatively clean, we have a lot more solar power and even wind power than many parts of the US. That means that transportation in the blue here accounts actually for over 40% of the emissions. And so, yeah, so this is kind of the problem, right? And electric vehicles is going to be helping with the solution for part of this sort of blue portion, just to help kind of put it into perspective. There's a lot of other things that need to happen, and we're not going to really talk about that too much in this class. But electric vehicles are going to be an important sort of technology contribution to reducing those emissions down, hopefully to zero in the next couple decades. All right. So that's kind of the background for a lot of my motivations. Any questions here? I'll stop for a second. Okay. So today, what we're going to do is going to be covering a lot of sort of basics about energy and power, and some basics about the vehicles themselves to get us sort of situated so that we have a good foundation to work with. This is going to be kind of really important to understand a lot of the things that are going to be happening and that we'll be talking about regarding technology in the next couple lectures. So if anything's confusing, feel free to ask me to slow down or repeat anything. For some, this is probably going to be a pretty easy review, but for others who are sort of less comfortable with the stuff, we'll get this drilled in during the class. Okay, starting off, what is energy? So energy is the ability to perform work, to either, we usually refer this as to move an object or to heat an object. Okay, and there's a bunch of different forms of energy: kinetic, chemical, heat, electric, electromagnetic, elastic, nuclear, gravitational. We're going to be talking actually quite a lot about the first five, but not too much about elastic, nuclear, or gravitational. Okay, energy in terms of joules. So this is the gold standard for measuring energy, or for sort of quantifying energy. This is the international standard unit for energy. And this is used across basically a very sort of wide variety of both applications and fields. So the definition of 1 joule is that it is able to heat 1 gram of water by 0.24 degrees Celsius, or the equivalent is to move a 1 kilogram of weight a distance of 1 meter with an acceleration of 1 meter per second squared. Yeah, and so this this unit is going to be very sort of common in a lot of the discussions that we're going to be talking about, but we'll also be talking about an equivalent source of energy that's more common in electricity in just a moment. Before we get there, I want to talk a little bit about power. So power is just energy over time. It's the rate of doing work. And the two main units of power that we're going to be talking about in this class are watts and horsepower. Okay, and so what is a watt? The SI unit for power is 1 watt, which is 1 joule per second. And so if you think about that quantity of energy that I was describing with 1 joule, 1 watt is basically that amount of energy being exerted every second. Okay. So this is most commonly used in electricity. So we might describe like the capacity of a power plant, for example. So if you have what I'll say is an installed capacity of like 10 megawatts, that means that that power plant can at any point in time produce a maximum of 10 megawatts of instantaneous power. The other one, so if folks are used to hearing about cars, this unit of power, known as horsepower, is usually used to describe the power related to engines, right? And so, you might say, oh, my car has, 100 horsepower, right? And so that means that it is able to have a maximum energy output at that rate of horsepower. So the strict definition of a horsepower is being able to lift a kilogram 1 meter in 1 second, or 75 kilograms 1 meter in 1 second. I'm going to make it a little bit confusing here. There are sort of 2 metrics for horsepower. There is an imperial version and a metric version. I don't know why they did this, just to make life confusing for students. 745.7 watts is 1 horsepower in imperial. 735.5 watts is 1 horsepower in metric. They're pretty close. So you're not going to go too wrong by using either of these. Just know that very often, if we're working in the US, they're typically referring to this 745. But if you're in other parts of the world, they'll be using the lower number. Okay, so quick question. How much horsepower do you guys think a horse has? It's actually about 15. So horsepower doesn't even really kind of refer to the power that a horse could output. Yeah, so again, still a little bit confusing. Okay, so this is going to be the most common unit of energy that we kind of use in this class, and that's because most of the electricity world measures things in this set of units, and electric vehicles have sort of followed through suit. And so when I talk about like the capacity of a battery for an electric vehicle, it's going to be measured in kilowatt hours. Okay, so pay attention here because students get confused about this all the time, and it is a little bit counterintuitive. So remember, watts are a unit of power, which is a rate, but energy is just a sort of specific quantity. And so if you remember that a kilowatt is per unit of time, you're multiplying by hours. So the units of time cancel out and you get a unit of energy. And so most commonly used in electricity, this is measuring the amount of energy used at a constant power rate over a period of time. So if a light bulb, for example, if you're using, say, a 5-watt light bulb and you turn that light bulb on for 1 hour, I could go back and calculate, right, 5 watts times 3,600 seconds, which is the number of seconds in an hour, and do that calculation to get the number of joules. Or I could just say 5 watt hours, okay? And those two numbers are equivalent. So 1 watt hour is equal to 3.6 kilojoules, and that 3.6 kilojoules is, right, 3,600 joules, which is just the 3,600 seconds there are in a second. Or sorry, in an hour, not in a second. Okay. So for folks who have seen these meters or sort of more modern day meters, they're often read in these units in kilowatt hours. So like consumption of electricity at the residential level is very often sort of measured in kilowatt hours. And so you'll have to start getting comfortable with converting sort of kilowatt hours back and forth to sort of different units throughout the course here. All right, is anyone confused yet about this? Any questions? All right. So let's get right into some practical examples. Battery energy and vehicle range. So the other sort of concepts that we're going to need to get familiar with are, what are the sort of analogous things that we talk about in reference to gas vehicles compared to electric vehicles. Okay, so here we've got a Toyota Camry, which has a 15.8 gallon tank. So it can hold about 16 gallons of gasoline when you fully pump it. And it can go 537 miles with a single tank. So who can tell me how I would calculate the efficiency of this vehicle? Yep, exactly. So if you guys remember, so I'm sure you have heard of miles per gallon. So all you have to do is arrange those units in that way. So 537 miles in 15.8 gallons. And this is going to give me some number for MPG. And that tells you kind of roughly how efficient this vehicle is going to be. And don't worry, we're going to have an entire lecture talking about sort of these numbers, like how you get this 537, how this number is calculated, what it means for like an EPA rating. We'll get into all that stuff. So similar to gas cars, electric vehicles also have these comparable sorts of measures for essentially the energy capacity and the range of the vehicle. Okay, and so here we've got the Tesla Model Y, for example, which has a 75 kilowatt hour battery compared to all these other guys. So 68 kilowatt hour battery, 60 and 40, and they all have sort of different ranges here as well. So we're out of the realm of being able to talk about tanks of gas, right? Now we're talking about the capacity of these batteries. Likewise to this calculation, you can also figure out the efficiency of an electric vehicle using kind of the same measure by dividing. Okay, so for this Toyota Camry, if you do this division, 34 miles per gallon. And we can now kind of do the same thing for these vehicles. So if you're used to kind of the nomenclature for gas cars, you might envision a range of like 15 mpg for like a really sort of inefficient gas car, maybe like a big truck or something. I guess a Hummer gets what, like 10 to 12 mpg, something like that. And then on the other end of the spectrum, you can get up to, I think the Prius is the highest these days at like 55 to 57 mpg. Okay, and so for vehicle efficiency, we're talking about the same thing here. And I actually have two ways of showing this. So let's ignore the one on the right-hand side for a second. So this mile per kilowatt hour really is the sort of equivalent for gas cars. You're describing a distance traveled by unit of energy. And so if we look here, you're talking about sort of on the order of 4 miles per kilowatt hour down to, so for this one, 3.1 miles per kilowatt hour. That's actually still, I think, still relatively efficient. I think the least efficient electric vehicle on the market these days is the Jaguar I-Pace, which I believe is sort of on the 2.5 miles or so per kilowatt hour. So that just gives you some idea about the sort of range again, similar to gas cars. On the right-hand side, I have units displayed in a slightly different way. So this is just the inverse. It's the kilowatt hours per mile. So if you thought about what that would mean for a gas car, that would be putting the sort of gallons in the numerator instead of the miles. Anyone here not from the US? One person. Really? All right. Okay. Oh, okay. A couple people. Sorry, didn't see the hands. Okay. How do you guys measure fuel efficiency not in the US, wherever you guys are from? Kilometers, yeah. Liters, yeah. But when you see like a car commercial or something for in your country, do they say liters per do they say liters per kilometer, or do they say kilometers per liter? Oh, okay. Interesting. Yeah, so yeah, I guess some places will still do that, but most, actually, the rest of the world goes by different units. They use liters per 100 kilometers. And functionally, these can be sort of directly translated into one another. But we're going to talk a little bit later on about the sort of intuition behind doing it sort of one way or the other. It's actually a little bit counterintuitive. And so for electric vehicles, people have also started to do it this other way, which, sort of disclaimer, I'm just going to say I like this second way better, and we'll talk about why later. But to give you a sense of what the ranges for that looks like, it's going to be the opposite, right? So the lower the number in the numerator, the more efficient the vehicle is, as opposed to MPG, right? You want high MPG. For gallons per mile or for kilowatt hours per mile, you want lower. And so those are going to range from around 0.25 on the sort of more efficient end up to about 0.45 on the sort of less efficient end. And again, you can translate between those two in a pretty sort of straightforward way. But again, we're just trying to get comfortable with these numbers and the way we think about them. Any questions about this? Any confusions about efficiency? We all know how we get to this number. Great. Oh, yes. Uh-huh. Yep. Yeah, yeah. Great point. Yeah, and we're gonna delve into that quite a bit actually later on. But I guess what I would say for now is, well, let's think about kind of real world application here. So California back in 2007 was AB 32. Is that right? 2007, 2006. I was in high school then, so you'll have to forgive me. So 2006, we had this policy called AB 32, which says, okay, California, you have to reduce your total emissions down to 80% below what you had in 1990 by 2050. Okay. No, you shake. Yeah. And then the add-on, right, was to do 80% below by 2050.
It actually probably was 20% less than what it was at the time.
Yeah. 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 So that's this kind of high level overarching goal to reduce our emissions. And the problem is, okay, so there's this thing where, okay, if you were to fully decarbonize transportation, let's say you put all of these guys onto electricity grid. Let's suppose, for example, that they don't contribute to electricity at all, and you just decarbonize all the all vehicles. You wouldn't actually be able to still hit the goals of the requirements by 2050. You'd still need to reduce all the other sectors. And so at a high level, kind of the motivation is, yeah, these guys might be increasing sort of electricity demand, but at the same time this is happening, you have to have policies in place to clean your electricity grid too. So that's kind of why this works, right? What I would say is that even today, if you switched like every car in the US to an electric vehicle, you will still end up being cleaner than you had sort of gas cars, but it would put a lot of, let's say, kind of extra demand on the grid, and you would have grid emissions, particularly in places that still use a lot of fossil fuels, natural gas, coal, for example. But the idea is that all of those sort of end sources are going to get clean over time as well. Yeah. But that's exactly the kind of thinking that you need to have to be able to sort of holistically make these policies and think about, not just think about sort of transportation in isolation. So good question. Anyone else? All right. So again, I think, yeah, what we're doing here is we're still kind of going through some of these basics and hitting a lot of sort of foundational points of things that we're going to get into a lot more detail down the line in other lectures. Okay, so here, charging power. So you may have heard, right, that if you use an electric vehicle, unlike a gas car where I can go to a gas station and just fill it up at the pump, it actually takes a little bit of time to refuel your vehicle. And again, we'll talk about kind of the implications of that, maybe why it's not as bad as you might think. but just in terms of kind of understanding the power and energy units that we're going to be working with here, right? So chargers will put out energy at a specific rate, and so we're going to be talking about charging in units of power. There are a couple sort of different levels of charging that we'll be talking about. So there's level 1 and level 2, and then there's DC fast charging, which is going to be sort of all of these three. So that's what DCFC stands for, is DC fast charging. And sort of a little bit more nuanced, there's Tesla superchargers, which are a little bit different. And then these days there are a whole suite of what some people dub as extreme fast chargers. It's not really kind of official nomenclature, but there's a lot of different ways people talk about this, which is like super high power. So a level 1 charger is something you could just plug right into any old outlet over here. And that charges at a rate of 1 kilowatt. So consider that you have an electric vehicle with a 75 kilowatt hour battery. If you plug that in with a level 1 charger, then in theory, to get to 75 kilowatt hours, right, you'd have to go at a 1 kilowatt rate for 75 hours. So you can divide 75 kilowatt hours by 1 kilowatt. So let me just write that over here. So whatever my battery capacity is, 75 kilowatt hours. If I divide that by kilowatts, this unit of kilowatt cancels out, and you're left with hours. So that tells you how long it would take. So at level 2, which is anywhere between, say, about 6 kilowatts all the way up to, in theory, 20 kilowatts, that will charge it at slightly faster rate. So if I do 75 divided by 7, you're talking about on the order of 10 hours. And then for these three, which are charged using a slightly different form of electricity, we'll say 50 kilowatts, you can do it in about an hour and a half, 120 kilowatts, about 40 minutes. And then this is a Porsche Taycan. It's one of the few vehicles that can go at that high of a charging rate, although these days there are more and more that are able to do that. So this is charging at 270 kilowatts. So it can fully charge this 75 kilowatt hour battery in about 15 minutes. Okay, so there's a lot of nuance here that I'm not talking about yet, and we'll get into it. It actually isn't able to, like, cars can't actually charge sort of at this sort of continuous pace for the entire sort of range of the battery. So this is like a oversimplification, but this is more just to get us comfortable with the units for now. Okay, any questions about charging? Yes.
I've got a car that has about 75, 80 kilowatts.
Yes.
That's I've never close to 40 minutes.
Yes, I know. Like I said, there's some nuance here. And we'll talk about the specifics when we talk about the charging infrastructure and when we talk about the batteries. So one of the things is that as you charge your battery, the voltage actually changes, right? And so that's going to affect the rate at which electricity can go into the vehicle. And for that reason, you typically won't see this exact kind of effect. But again, this is just to get familiar with the units. Dan, how long does it take you to go from like 0 to like 80% of the vehicle? About an hour. Yep. And the kind of rough rule of thumb that we have, which is, again, also has a lot of nuance, not always true, but the amount of time that it takes to charge from 0 to 80% of your battery is about the same amount of time that it's going to take to charge from 80% to 100% of your battery. So that last 20% is like extra hard to do. Is that kind of align with what you find? Yeah, okay. And again, depends on the battery size and conditions and so on and so forth. Great. All right, any other commentary about this or questions? Okay, yeah, it's a lot less straightforward than filling at a gas station. But what I like to tell people, like who here likes going to a gas station? Anyone? See, with an electric car, you don't have to. All right. So let's get into some EV basics. Actually, why don't we take a quick like 5-minute break here? Yeah, folks can use the bathroom, get up, walk around if you want. Back to the lecture. So EV basics. All right, guys, settle down. Yeah, I can tell. So EV basics, and we'll probably actually end a little bit earlier today, which will be good. Yeah, so what I wanted to talk about briefly for the rest of the lecture is nomenclature that we'll be talking about. So this is pretty simple stuff. So this is what we're going to be calling our sort of traditional gas cars. People refer to these as ICE vehicles or ICVs, just referring to the internal combustion engine. Okay, so these vehicles are powered by the combustion of fossil fuels, most typically gasoline, but also there are some versions, right? You can use diesel. There are even some vehicles that combust natural gas, and some vehicles that combust ethanol, biofuels, that sort of thing. Okay, and so principally, we're going to talk a little bit more about drivetrains, and we'll even talk about gasoline drivetrains in a little bit. But the general components that you're going to find consistent across these vehicles, you've got your engine and a sort of fuel tank. Those are the sort of bulkiest components of your ICV. From the engine, you also have for the byproducts of combustion going through an exhaust system, and that includes a catalyst that will help sort of reduce some of the air pollution from combustion byproducts, as well as a muffler to kind of keep that a little bit quieter. And then from the mechanical energy coming out of the engine, that's translated through a transmission system. And the transmission is just making it so that the sort of rotation of your crank and camshaft are translated differently into the wheels. So transmission going to ultimately your drive shafts into your wheels. And obviously, sort of the fueling compartment is going to be sort of different. I think most people, right, are familiar with how that works. Okay, so the first point of sort of common confusion, and oh, sorry, yes, go ahead.
Out of curiosity, what's the 85?
Yeah. Okay, so today when you go to the gas station and you fill up gas, it's not just pure gasoline. About 10 to 15% of that, depending on what sort of state you're in, is actually ethanol, which is just right your alcohol. There are some sort of like political reasons for why this happens. It supports a lot of agricultural industry, that sort of thing. But it turns out you can mix ethanol with gasoline and use it in regular engines without really any problem up to kind of a certain percentage. Past that, you start to need some modifications to the vehicle, and they're actually not even that extreme. There are certain like gaskets and that sort of thing that they use different materials to prevent corrosion, because ethanol can corrode, that sort of thing. And so E85 is 85% ethanol and 15% gasoline. It's very rare. It's rarer to find stations that have that, especially on the coasts. They're a little bit more common kind of in the Midwest, but even then it's mainly E15. So ethanol we consider kind of majority sort of biofuel. And not really sort of gasoline. And those can be used in vehicles known as flex fuel vehicles, which there are actually millions of in the US, but most of those flex fuel vehicles are just driving on regular gasoline. Yeah. Does that answer your question?
Because I knew that like, the ethanol content on the different grades of gasoline is 91 to 9.
Yeah. Oh, okay. So okay, no, actually, so that's actually something different. So when you go to the gas station and you see like the 3 buttons, and it's like, it can be 91, 93, 95, 97. So this is actually known as an octane rating, which is different from the ethanol rating. This refers to the proportion of hydrocarbons which are C8 in the sort of fuel mixture. And yeah, I'll talk about actually what this means when we're talking about the sort of when we're talking about the specific drivetrain for gasoline vehicles. But this is a little bit different from the ethanol thing. Yeah. Okay. Any other questions? So you guys all kind of self-selected into this class. It's not like a requirement. So I would imagine maybe that means folks are generally kind of more familiar, but this is actually one of the biggest sort of public misconceptions about electric vehicles. So hybrid electric vehicles is not something that we would typically describe as an electric vehicle. Okay, so what is the distinction? So an electric vehicle is something that can propel itself entirely on electricity through its drivetrain, which is not entirely the case. Well, it's definitely not the case with HEVs, sort of with a little asterisk at the end. So hybrids, so the one that most people think of, right, when I say hybrid, is like a Toyota Prius. So these are gas cars. If you drive a Prius, you know that you fill it up with gas, you don't charge it. You don't charge the battery like you would with an electric vehicle. The reason why we call it a hybrid is because there are features about the drivetrain that are similar to electric vehicles that allow it to improve its fuel efficiency. So the two, so one of the big things that I actually don't have here listed is the fact that these guys have a pretty substantial battery as well. But the battery is not sort of directly just powering the drivetrain. Okay, so the caveat is that modern day hybrids, if you're driving like the newest Prius, you can drive just on the battery for like a mile if you're going under like 15 miles per hour, right? So there are these like little things that, okay, it's kind of like an electric vehicle, but generally speaking, for everyday driving, you're not going to be able to do that. But they have these really important features that really help with fuel efficiency. So the first one is regenerative braking. So for a gas car, you hit the brakes, and usually you've got these like rim brakes or drum brakes that basically clamp down on your wheels, and friction causes your car to come to a halt. And all of the energy from the motion is going into heat from the brakes on your wheels. In this case, it's different. The energy from the motion is going back into a generator, which is used to produce electricity that then gets stored into your battery. And so all of that energy that you would usually lose as heat, you get back in terms of energy stored within the battery. When you look at like EPA ratings for fuel efficiency, they usually break it down by city driving and highway driving. And usually highway driving will have a higher number than city driving. And the reason for that is because you're driving around in the city and you stop a lot, right? You get to an intersection, stop sign, stoplight, whatever, and you're constantly sort of losing energy that you put into the car. But if you look at EPA MPG ratings for hybrids, a lot of times those numbers might be as high, or even in some cases higher than the highway MPG, because of this exact process. The other thing is that also when you're in the city and you're constantly stopping, so I go to a stoplight and I'm sitting there for 2 minutes, and my engine's still running, even though you're not moving, there is fuel that's getting combusted, and it's not translating into sort of useful energy, right? It's all just getting sort of lost as heat. So with hybrids, one of the things that they do is they have a sort of really specialized start-stop system, which is kind of shown in this diagram. And this shuts the engine down when you're at like a stop sign or a stoplight and you're not operating the vehicle. And so that can help quite a lot as well. And idling can use quite a bit more energy than people realize. Yeah, one of the things that we had talked to with actually the LAPD, does anyone know what the average fuel efficiency of a cop car in Los Angeles is? Anyone care to guess? 18, 14. Yeah, so actually it's like 1, because they're just idling all the time. They have to keep their computers powered and that sort of thing. But it's pretty insane, right? And so these kind of systems, even to hybridize their vehicles or go to an electric car, would save a huge amount of money for use cases like that. Yes. Yes, we're gonna, that's exactly what we're gonna cover. We wanna get all that through all that nomenclature. Yeah, so there's ICVs, there's HEVs we've covered so far, hybrids. We're gonna talk about EVs, PEVs, PHEVs, which are plug-in hybrids, and then BEVs, which we're going to call sort of as battery electric vehicles. So again, there's lots of people use different sort of terms, and we just want to be sort of super clear about what all of those mean. Okay, so hopefully there won't be any confusion by the end. But if there is, just whoa, hang up, like, let me know. Okay. So again, it's a new technology, and the consistency in like the academic literature, like people doing studies, much less even talking about the way media might talk about it, or bloggers, forums. it can all get kind of sort of hectic. And so I'm trying to sort of outline what we consider the sort of standard terms for these things. So EV, PEV. Electric vehicles are vehicles whose propulsion is powered by electricity rather than the combustion of fuel. And plug-in vehicles are a subset of electric vehicles, which means all PEVs are EVs, but not all EVs are PEVs. So plug-in vehicles have batteries that are charged by plugging the vehicle into a charger. Okay, so if PEVs are EVs, but some EVs aren't PEVs, what are the things that aren't PEVs? Those would be, the most common would be fuel cell vehicles, which operate their drivetrain on electricity, but don't need to plug the vehicle in to run the vehicle or to charge a battery. So we will talk a little bit about fuel cells, but again, the main focus of the course will be on electric vehicles. If people have specific interest in fuel cells, we can get into it, but we won't go that deep into that technology. Okay, so next guy, so battery. So we're going to talk about the subset of PEVs. And so there's two main guys under there. The first one is, I think, the more straightforward one. So this is your battery electric vehicle, BEV. So this refers to, I think, what most people think of when we talk about electric vehicles. It's just a car that operates basically entirely on electricity powered by this onboard battery. So this is what your car looks like. You've got your battery pack instead of your fuel tank. And then you've got your basically your motor here, which is driving this thing. So we'll talk about some of the benefits of structuring it this way, but one of the big things is that there's very few moving parts in a battery electric vehicle compared to a gas car. So in a gas car, you've got pistons, which are moving and exploding fuel, which turns a crankshaft, which turns a timing belt, which turns a camshaft, which operates a set of cams. And then the crankshaft goes through a whole transmission system, which then goes through your drive shaft. Here, it's the moving parts are your motor and your drive shaft, and that's it. Okay, so a lot fewer things moving means maintenance issues are going to be sort of a lot lower. And again, that's something we'll talk about later on in class. But you can see sort of holistically, from the outside, the car looks pretty similar, but the guts of it is going to be really quite different. Yeah, there's no fueling port. Back here, you've got usually sort of a charge port. Not very well standardized these days. So for a gas car, it's usually on the back right or back left. For a BEV, right now, it can be in the front right, front left. It can be off here in the grill. It can be in the back right, back left, and then Tesla even has it coming out of the lights. So yeah.
So I hear a lot about people are interested in going fast in electric vehicles.
Yep.
Talk about instantaneous torque.
Yep.
So is that type of thing happening because there's so few parts in comparison to a gas car?
Partially. We're gonna hit that topic actually in the third lecture next week. So we'll get to that. But exactly. So torque is basically how much you're going to feel the force coming out of the vehicle. And EVs, so to put it really shortly, the reason why the torque is effectively so much higher in electric vehicles is because it doesn't have to go through all of this other sort of moving parts. There's less sort of friction, and it doesn't need to build up. So if you imagine the way an engine works, right, with pistons going up and down, it takes a little bit of time for you to get the sort of combustion process going in an efficient way that your power output is kind of at like peak engine performance. Whereas with a motor, it's like spin it up and you can just go at whatever level that you want. And so EVs are going to definitely accelerate quite a bit faster than gas cars. Okay, so the last one for PEVs, it's probably the most confusing. So someone was asking about this. So plug-in hybrid electric vehicles. So a plug-in hybrid PHEV is a type of PEV. It's not just a hybrid because it operates with its electric drivetrain, right? But it also has all the things that a gas car has. So this is essentially the combination of an internal combustion engine vehicle and a full battery electric vehicle. You've got the engine and gas tank, but you also have the motor and the battery. Unlike hybrids, they can operate solely on electric power without the engine turning on. So the let's say the top 3 models for the plug-in hybrid. So you've got the Honda Clarity plug-in hybrid, which is discontinued. The Chevy Volt plug-in hybrid, which is also discontinued, and the Prius Prime. The first 2 that I was talking about have about a 50-mile range, so much lower than this 300-mile typical type of thing that 200 to 300-mile typical thing you see in battery electric vehicles, right? But when it runs out of energy in the battery, it can switch the engine on, or you can choose to turn on the engine sort of at any time. And that gets around some of the like range anxiety issues that people talk about in reference to electric vehicles. And maybe even the sort of charging issues, like if you wanted to go from NorCal to SoCal, you don't need to stop for like an hour to charge the vehicle. So those are some of the reasons why people might want to prefer this type of thing. And we'll talk about this again later on, but in terms of travel behavior, you can still get, even though it's like only a 50-mile range, you can still get a huge portion of your driving on electricity when you use this vehicle. And so why is that? So the average American drives about 30 miles a day, which means, well, I can do all those, short commute trips, grocery runs, going to the movie theater, all of that kind of thing. You could just do on electricity and then charge back up and really use the gas kind of as a backup. Okay, and we'll get into all of those kind of behavioral things a little bit later on, but those are some of the motivations for why people use this kind of system. Yeah. So the Honda Clarity is kind of an interesting vehicle. It's kind of like a prototype test vehicle. It's not a test vehicle per se, but there was a Clarity for a fuel cell version, a full battery electric version, and a plug-in hybrid version. And it's a way for Honda, I think, to kind of test out the technology. I think it was never meant as like a large volume production vehicle. And so it wasn't sort of that surprising that that was halted. The Volt, also a really sort of popular plug-in hybrid. So there are a lot of, I think, sort of deeper reasons why that one ended up getting stopped, but I can't be entirely sure why. I mean, I can kind of give some hypotheses, but one of the reasons might be that Chevy is kind of going maybe, or GM is maybe going sort of all in for a full battery electric lineup, and they just don't want to bother with producing what some people might argue is kind of like a half-baked measure. Yeah, and there's probably still a role for these types of vehicles. When we talk about use cases, electric vehicles truly might not be able to be compatible for all use cases for everyone. And so when we talk about a world in which you can no longer buy like a pure gas vehicle, it may be necessary to have these types of vehicles for certain types of drivers and for certain types of use cases. We'll talk again in a little bit more detail about the sort of configurations, right? Like how does the engine and the motor work together? Do they go at the same time? Does one have to go through the other? How does that work? So there's a bunch of different configurations of these that have been sort of tested out in practice with different types of vehicles. And so we'll cover all of that in another lecture. Okay, any questions about this thing? You can see it's like quite crowded, right? You've got a fuel tank and a battery pack, and then you've got your engine and the motor back here, and then all the sort of associated like control mechanisms. So like you still have to have your converter, but you also have like your transmission, electricity, electric generator. Yeah, and so these are definitely the most complex because you have to have all the components of both systems. Oh, and we're gone. All right, we're back. All right. Okay, so the last one, fuel cell vehicle, again, not a plug-in hybrid, but it is, or sorry, yeah, not a plug-in electric vehicle, but it is an electric vehicle. So FCVs, fuel cell vehicles, they employ a fuel cell to oxidize a fuel to generate electricity. So this is different from your gasoline car, which combusts gasoline. The most common fuel cell vehicle is the hydrogen fuel car. But there are other types of fuel cells. There are natural gas fuel cell vehicles, for example. Modern day hydrogen fuel cell vehicles also will have a battery, but it's not meant to be sort of charged externally, as I was saying. This is kind of in a similar vein to the way hybrid vehicles work, where they can employ the battery to do things like regeneration, regenerative braking. Configuration of these guys is definitely a little bit different. So you've got your smaller battery pack here, and then the fuel tank here. It's definitely a little bit more complex than a regular sort of gas tank where you could just fill it up with gasoline. These things have pretty intricate designs. Depending on the way that it's configured, you could store hydrogen at extremely high pressures, which can be, which requires some pretty robust design. You could even store it in some, well, not in sort of any practical current commercial applications, but like hydrogen can also get stored as a liquid, which is one possible way of storing the fuel. And that will go through your fuel cell stack here, which translates essentially your hydrogen to combine with oxygen to produce water. So water is the byproduct, and that process is exothermic, which means it releases energy. In a fuel cell, you're going to capture that with electricity, which is what makes it an electric vehicle. So I should mention, actually, if I go back, so for a battery electric vehicle, there are no sort of byproducts, right? There's no exhaust pipe. It's all just electricity going through the motor. But with a plug-in hybrid, you do have an exhaust because you are still combusting gasoline in some instances. So with a fuel cell vehicle, your byproduct is water. And if anyone's like driven in like a Mirai or something, there's actually a little button you can press, and the car will just squirt out water out of the back, just onto the road. But also doesn't really have like an official tailpipe type of thing. Yeah.
So the first thing that came to mind when you mentioned high pressurized hydrogen is
that that car gets in a crash, we don't know, like, explode.
Yeah, so the design of these things is actually pretty robust. Like the hydrogen can escape, and because it's so low density, typically it's just going to go out into the atmosphere. Yeah, it's actually one of the most common things that people talk about when they think about these fuel cell vehicles. Is like, oh, like the danger associated with that. And I'm not gonna like dismiss it. It's like, it's true. Hydrogen combustion is dangerous. It's actually extra dangerous because if you combust hydrogen, it's colorless. So if there's like a leak and it's on fire, you won't see it. You'll just put your hand through it and you'll get burned. But you know, gas cars are filled with flammable liquids too. So I would actually argue that a gas car is more dangerous because like the liquid hangs around, right? And it can catch on fire. Whereas this stuff, it's under pressure, which means that it'll get ejected into the atmosphere very sort of quickly. Yeah, but not gonna say that there isn't like some potential for explosion. I think the chances is probably lower than people think. Yeah, and similarly, you know, with batteries, you are talking about these like materials that are very energy dense. There are many examples already of sort of battery fires, but I think the real question is like, what is the rate of incidence for those types of things versus, you know, like combustion events or things going wrong with a gas car, right? So that's one thing to think about. Yeah.
The things are actually made out of carbon fiber, just to kind of show how tough they were. They actually shot them.
Yeah.
They're bullet. So, like, imagine an accident. Pretty unlikely that it's gonna rupture. They kind of designed it to the main failure mode. So
Yeah.
it's possible that in an accident there could be leaks, but the idea is it's very light gas. So
Yeah.
it's not like
Yeah, it's gonna make our future Hollywood movies a lot less climactic when people are like shooting at the cars and they don't explode. Okay. Zero emission vehicles. This is more of like a policy type of term, but just want to clear up the nomenclature here as well. So this is any vehicle that has essentially no tailpipe emissions. So BEVs and FCVs are both ZEVs, but not all PEVs or EVs are ZEVs because plug-in hybrids are not zero emission vehicles. They have a tailpipe, they can operate on fossil fuels. So there's like a really weird set of like Venn diagrams for all of these terms, which looks something like this. Okay, so you've got your internal combustion engine vehicles here, of which your HEVs are, your hybrids are a subset of those guys. And then you've got your full set of electric vehicles here. And within those, you've got your FCVs, PHEVs, and BEVs. The BEVs and the FCVs are zero emission vehicles, no tailpipes, no emissions. And then your PHEVs and BEVs are both plug-in. They have batteries. They need to charge by sort of plugging them in. Yeah, and these are just a sort of couple examples of models that fall into these categories. Maybe you've seen some of these, maybe not. Yeah, but the sort of body of number of vehicles is going to sort of continue to grow into the future. Okay. Confusions, questions? Great. Okay, I think that's actually all I have for today. So we're going to end a little bit early. I have this sort of like reference slide at the end for folks here. But otherwise, yep. So I'll see everyone next on Wednesday at 5.